In this video, we're going to continue our discussion on functions to learn about some operations on functions. So by operations, we mean our standard operations that we know from algebra, things like adding and subtracting, multiplying and dividing. However, with functions, we also have another operation called composition, which we'll learn about in this video. And we're also going to learn about one very special thing with functions called the difference quotient, which is going to come up again very quickly when you're in a calculus class. So it's very good to pay attention to that part. So let's get started. So given two functions f and g, we're going to define some various operations. We have f plus g of x is the function defined by f of x plus g of x. And f minus g of x is f of x minus g of x. The function f times g of x is f of x times g of x. And the function f over g of x is f of x over g of x, provided that g of x is not 0, because of course we don't want to be dividing by 0. All of these standard operations here work exactly the way you want them to, which is very nice. So when you're adding two functions together, you literally just add them together. When you multiply them, you multiply them. The only one that's a little bit complicated is the division, because you just have to make sure you're not dividing by 0. But other than that, it works exactly the way that you would like. Now, when we talk about functions, we usually talk a lot about the domain of the functions. And we need to talk about the domain of these new functions here too. Domain of all of these depends on the domain of the original functions. So the domains of f plus g, f minus g, and f times g all of those domains are the intersection of the domains of f and g. So when you're adding two functions together, subtracting them, or multiplying them, the domain of that new function is based on the overlap between the domains of the two original functions. Now, when we use the quotient dividing, it's a little bit different. We have the intersection, but we also have to exclude values that make our denominator 0. So for the function f over g, we also have to exclude values for which g is equal to 0. So the domain for f over g is just slightly more complicated. It's still the intersection of the two domains, but then you also have to exclude any values that make you divide by 0. Sometimes there aren't any that make that happen, but sometimes there are. So let's do an example where we try out all of these different operations. So example, for f, which is negative absolute value of x, and g, which is 4, we're going to find all of these different combinations of functions. We'll start with f plus g of x. So remember, f plus g, all that means is I just have to add my f and add my g together. So my f was negative absolute value of x, and g is 4. So f plus g is negative absolute value of x plus 4. The difference of the two functions is done very similar. It's just I have to subtract 4 because I'm subtracting the function g rather than adding it. The function f times g, it's just as simple as multiplying the two functions together. So negative absolute value of x times 4 would get me negative 4 times absolute value of x. And then for the last one, let's take a look at f over g. So I would have negative absolute value of x over 4. Not too bad. It's just a matter of writing them in the right places and performing the correct mathematical operations. Let's do another example. Let's get some new functions. We have f, which is x plus 3, g, which is x squared minus 9, and we'll have h, which is square root of x plus 1. And the first thing we're going to do is find f times h of x and write the domain in interval notation. All right, so let's first find what the function actually is. So f times h, we just have to multiply our functions f and h together. So that would be x plus 3 times the square root of x plus 1. And that would be the function f times h. Now to find the domain, remember the domain of f times h is going to be the intersection of the domains of f and h. So we need to find the domains of f and h first, and then find what the overlap is. So my function f was x plus 3. So the domain of f was just all real numbers, negative infinity to positive infinity. Because x plus 3, you can plug anything you want into it, and you're not going to have any problems. We're not divided by 0, and we don't have any square roots of negatives, so it's all good to go. For h, my function h was the square root of x plus 1. And we know that we need to have, underneath a square root, we need to have a non-negative number in order to take the square root when working with real numbers. So the domain of h is found by taking everything that was under the square root and setting it greater than or equal to 0. When I solve that, I get x is greater than or equal to negative 1. So the domain of f times h is where these two domains overlap. Well, one of the domains is literally all of the real numbers, and the other one's just talking about real numbers greater than or equal to negative 1. So they overlap as every x greater than or equal to negative 1. So my domain of f times h is every number greater than or equal to negative 1, which in interval notation, we start at negative 1 with a bracket because we have that equal to, and we go all the way up to infinity. Let's do a slightly harder one. We're still using the same f, g, and h that I had written down before. So part B, we want to find h over g of x, and also write the domain in interval notation. So h over g, remember, you just put the function h on top and g on the bottom. My h was that square root of x plus 1, and g, which I erased before, g was x squared minus 9. So this is my function h over g. Now to find the domain, this is the tricky part. So the domain of h, we just found, was all the x greater than or equal to -1. The domain of g, well, g is a polynomial, x squared minus 9. So its domain was all real numbers because we're not dividing by anything and we're not having square roots and negatives. So the domain of g by itself was all real numbers. So right now, I know the intersection of these two is still all of the x's greater than or equal to -1. But since I'm dividing, I also have to be concerned about any values that make me divide by 0. So my denominator g of x is equal to 0 when my x squared minus 9 is 0. This happens when x is plus or minus 3. So these values, plus or minus 3, are not in the domain. One of the values that makes the denominator 0 was already excluded from the domain because I already knew I needed x to be bigger than or equal to -1. So that -3 was already excluded. But this +3 needs to be excluded as well. So my domain is going to be all of the numbers bigger than or equal to -1 that are also not equal to 3. How do we write that in interval notation? Well, we just start with our smallest number. So domain of h over g of x is, we start with the smallest number allowed, which is -1, and we go until we reach a number we can't use, +3. Use a parenthesis to say we can't use 3. We continue from there all the way to infinity. So I get -1 to 3, not including 3, and then 3 to infinity, still not including 3. All right, so that's how we do a lot of our basic operations on functions. The trickiest part is just finding the domain. But as long as you remember the domain of all of these different function operations ends up being the intersection of the domains, and then you also make sure you don't divide by 0, you're good. So now we need to learn about something called the difference quotient. And like I said at the intro of this video, the difference quotient is something that's absolutely essential for calculus. Once you get to calculus, you're going to learn about something called a derivative, and you're going to see this difference quotient showing up in the definition of a derivative. We are literally going to be one tiny step away from calculus when we're doing these difference quotients. So what is a difference quotient? So the difference quotient for a function is the average rate of change for the function between the points x and f of x and x plus h, f of x plus h. So we learned average rate of change before. We know the average rate of change of a function between 2 points is just the slope of the secant line between those 2 points. So to find what this difference quotient is, we're going to have to find the slope between these 2 points. Don't be too concerned about this x plus h, f of x plus h, what's going on there. All this is saying is we're trying to take 2 points that are pretty close together. Think of h as some tiny positive number. We don't really know what it is, but this x plus h is just slightly to the right of this x. So using our formula for slope, we can write down what this difference quotient is. So our difference quotient is the slope between those points. So we had f of x plus h minus f of x over x plus h minus x. But this can be simplified. Notice the x and the minus x in the denominator subtract away to 0. So this is equal to f of x plus h minus f of x all over h. That is our difference quotient. And we're going to do an example right now where we find the difference quotient for a particular function. So example. Find the difference quotient for the function f of x equals 4x minus 2. So I would suggest, until you have it completely memorized, write down the definition for your difference quotient every single time. So I know I'm trying to find f of x plus h minus f of x all over h. So we have to fill in all the pieces. F of x plus h, remember that is your function, but with all of the x's replaced by x plus h. So I'm going to have 4x plus h minus 2. Then I have to subtract my f of x. So I'm subtracting 4x minus 2. And this is all over h. Now I would suggest you write it exactly the way I did here. Group your f of x plus h in a set of parentheses and your f of x in a set of parentheses. Otherwise, it's just way too common for people to forget that they're subtracting over here about halfway through their function. So I like to use those parentheses in my first step to make sure I don't lose a negative sign somewhere. Now we can simplify this. So what we're going to do to try to simplify this is we're going to distribute this 4 here. I'm also going to distribute this negative, and then I'll be combining like terms across the top and see what happens. So I'm going to get 4x plus 4h, I have minus 2, and then I have a minus 4x, and minus negative 2 makes it plus 2, all over h. And now take a look at what happens here. This is a good sign that you're calculating your difference quotient correctly. You should have a lot of things disappear at this point, have a lot of simplification. When I take a look at this, I notice that I have a positive 4x and a negative 4x. They're going to subtract away to 0. I also have a negative 2 and a positive 2, which subtract away to 0. All that I have left is 4h over h. But now I have an h in common everywhere. The h's can cancel out, and I just get a final answer of 4. So difference quotients usually simplify very nicely. After you've done your distribution and you're combining like terms across the top, you should have a lot of simplification. And then you should always look to see if there's a way to factor an h out to cancel with the denominator. Let's do another example where we find a difference quotient of a slightly more difficult function. So we're going to find the difference quotient for f of x equals negative x squared minus 5x plus 2. So let's remember again, what is our definition? F of x plus h minus f of x all over h. That is what we need to try to find. So let's do that. F of x plus h, again, I'm going to group it in some parentheses. That's what I get when I replace every single x with x plus h. So I get negative x plus h squared minus 5 x plus h plus 2. That's f of x plus h. Now I need to subtract my f of x. And again, I'm going to put my f of x in parentheses just because I know I personally sometimes forget that I'm subtracting about halfway through. This helps me remember to subtract every single term. And now all of that is over h. And now this looks pretty terrifying. There's a lot of simplification that can go on, but there's a lot we have to do, and we have to be very, very careful. So what we're going to do now, first I'm going to note that this x plus h in parentheses squared, that's the same thing as x plus h times x plus h. So that involves a lot of distribution right there. I'm also going to be distributing that minus 5, and I have to distribute this minus sign all the way through. So we have a lot of work to do. Let's see. Let's start by thinking of this x plus h squared. We know that this is going to be x times x, which is x squared, x times h, another x times h, so 2xh, and h times h, which is h squared. But I also have a minus sign in front of it. So let me just do the distribution and then take care of that minus sign next. So I have my minus, and like I said, x times x, x squared. X times h is xh. Another x times h is xh, so that's 2xh. H times h is h squared. I'm going to go ahead and distribute that minus 5. I get a minus 5x, a minus 5h, and a plus 2. And let's go ahead and distribute all of that minus sign here. So it's going to be a plus x squared, a plus 5x, and a minus 2, all over h. So before I start trying to combine some like terms together, let's distribute this minus sign into that x plus h squared that I expanded out. So all across the top, I'm now going to have a minus x squared minus 2xh minus h squared minus 5x minus 5h plus 2 plus x squared plus 5x and minus 2. That is a lot of stuff, and it's all over h. But remember, I said after you've distributed everything on the top and you start trying to combine like terms, we should have a lot of stuff disappear at this stage. And we do. I have a negative x squared and a positive x squared. Those will add to 0. I have a negative 5x and a positive 5x. I have a positive 2 and a negative 2. And nothing else combines together on the top, so let's just rewrite where we're at right now. Right now I have a negative 2xh, a minus h squared, and a minus 5h, all over h. And so now I look and see, is there any way that I can cancel this h in the denominator? Is there an h I can factor out of the numerator? And there is. All of my terms up at the top have an h in common. So let's factor an h out so that we can cancel the common factors. So I factor an h out of the numerator, leaving a negative 2x minus h and minus 5 all over h. And like I just said, now we can cancel our like factors of h to get a final answer for our difference quotient of negative 2x minus h minus 5. So that one was a lot more work than the first one, but sometimes you do have more complicated functions to work with, so it's good to get the practice in. So that is our difference quotient. And like I said, that is just one tiny little step away from doing calculus. You'll learn about it again, and This will look very familiar when you get into calculus and learn the definition of a derivative. So stay tuned for that. So we have one other operation we really need to talk about in this video, and it's called composition. So we need to talk about our function composition. Here's our definition. The composition of f and g which is denoted by the notation f with a little circle g is defined by f of g of x equals f of g of x. So the composition of f and g, when you see this notation here, you can either pronounce it as the composition of f and g, or you can say it the way I did when I wrote it, which was just f of g of x. And whenever I see this notation, I automatically rewrite it with the definition. That looks like I'm plugging one function into the other, because that's exactly what I'm doing. So this notation here is not multiplication. It is literally taking the definition for one function and plugging it into the other function. Now, what is the domain of a composition? The domain of f of g is the set of numbers in the domain of g such that g of x is in the domain of f. So what does this mean? It means first you have to only consider numbers that are in the domain of g, the function that gets plugged into the other one. That is your first consideration for the domain. And then you also have to consider if there's any point where the output of the function g ends up not being a valid input for the function f. So we're going to do an example where we find some function composition, and we're also going to get some practice finding the domain in our second example, just so that we can understand exactly what that means. But first, we are going to take two functions and find the composition at a specific number. So let's start with this example. So for the function f of x equals x squared plus 2x, and the function g of x is x minus 4, we're going to find a couple different things. The first thing we're going to find is g of f of negative 5. So when you see it written this way, you always want to start on the inside and work your way out. So when I look at this, I see that f of negative 5 is the very, very inside of this. That's the first thing I need to find. So we're going to find out what f of negative 5 is, and then we're going to plug the result into the function g. So f of negative 5 is equal to negative 5 in parentheses squared plus 2 times negative 5. This is 25 minus 10, which is 15. So what this tells me is g of f of negative 5, I can now evaluate as g of 15. So our g of f of -5 is g of 15. And now I can just plug that 15 into the definition for g. G was x minus 4. So this is going to be 15 minus 4, which is 11. So we started on the inside and worked our way to the outside. Let's do another example like that. So for our next example, we are going to use those same two functions, but we're going to find f of g of 9. And I wrote it using our composition notation. So the first thing you should do when you see this notation is rewrite it with the definition. I personally think it's a little easier to understand when it's rewritten. This is f of g of 9. So we need to start on the inside and work our way outside. The first thing we need to find is g of 9. G of 9 is equal to our 9 minus 4, because g of x was x minus 4. So g of 9 is 9 minus 4, which is 5. So that means that f of g of 9 is equal to f of 5. And now I can just take my function definition for f and plug a 5 in for all my x's. F was equal to x squared plus 2x. So I get 5 squared plus 2 times 5. This is 25 plus 10, which is 35. All right, on our next example, we're still going to be doing function composition. But rather than finding it at a particular input, we're going to find the actual function of one function composed with another one to create a new function. And we're going to find the domain of the new function. So an example. For f of x equals the square root of x minus 1, and g of x, which is 1 over x minus 3, we are going to find g of f of x, and we're going to write the domain in interval notation. So let's first find the function, and then we'll find the domain. So the function g of f of x, rewrite it using our definition. This is saying we're going to take the function f and plug it into the function g. So what I like to do is, from here, I replace f of x with what f of x is equal to. F of x is the square root of x minus 1. So we're trying to find g of the square root of x minus 1. And what does that mean? That means we need to replace every single x in our function g with a square root of x minus 1. So my function g was equal to 1 over x minus 3. So g of the square root of x minus 1 is 1 over square root of x minus 1 minus 3. And that is my function, the composition of g and f. So g of f of x is equal to this 1 over square root x minus 1 minus 3 on the outside of the root. And now we still need to find the domain of this function. Remember, the domain of a composition of functions is the domain of the inside function, which the result of that ends up still being in the domain of the outside function. So first, let's find the domain of the inside function, because we know we need to start there. My inside function was f. So start by finding the domain of f. F was the square root of x minus 1. We know to find the domain of the square root, we need to have, underneath the square root, we need to have non-negative numbers. So I'm going to take everything under the square root of x minus 1 and set it greater than or equal to 0. This tells me that the domain of my function f, the inside function, is all the values x which are greater than or equal to 1. But are all of those actually going to be allowed in our new composition? Maybe, maybe not. We have to take a look at what we have here. My actual composition, I need to make sure I'm not having square roots and negatives, and I need to make sure I'm not dividing by 0. Now, I'm not going to have any square roots of negatives because what's underneath the square root is already what I took care of when finding the domain of f. But is it possible to divide by 0 on this function? Yeah, it is. So I need to make sure I don't divide by 0. So we need our function f to be not equal to 3. Because if my function square root of x minus 1 happened to be equal to 3, then my denominator of this new function would have a 3 minus 3, which would be 0, and we'd be blowing up. So I need f of x to not be 3 to be in the domain of g. So let's find out when f of x is equal to 3. F of x was the square root of x minus 1. That equals 3 when x minus 1 is equal to 9. You get that by just squaring both sides. And this is true when x is 10. That means I need this x equals 10 to be not in our domain. So my domain is going to be all of the values greater than or equal to 1 that are also not equal to 10. So we just have to write that in interval notation. My domain of g of f is all of the numbers bigger than or equal to 1 that are not equal to 10. That means I get to start at 1 with a bracket, go until I hit 10, but then I use a parenthesis to not include 10. And then I continue on after 10 until I reach all of the possible numbers. So this is the domain of that function composition. All right, we just have 2 more composition examples to finish this video up. One is a word problem that uses function composition, and the other one is kind of thinking backwards with composition. I'm going to give you a function, and you have to try to break it apart into 2 functions that when you compose them, you get the original one. We'll do the word problem first. So our word problem, we have the cost to buy tickets for a show is $60 per ticket. Part A, write a function that represents the cost which we're going to call C of x for x tickets to the show. So this is kind of like one of our examples in an earlier video. Cost function, we know we can find by just taking the cost per ticket, multiplying by the number of tickets. So I know my C of X is going to be $60 per ticket times the number of tickets. That part's not too bad. Part B is where we start getting a little more complicated. Part B, we're going to start talking about including sales tax and a fee. So for Part B, there is sales tax of 5.5% and a processing fee of $8 for a group of tickets. We're going to write a function representing the total cost which we're going to call T of A for $8 spent on tickets. So the total cost, we're going to say we're spending $8 on tickets. I know I need to then multiply that to figure out the sales tax of 5.5%. And I also have a flat fee of $8 that has to get added on. So let's figure out this tax first. If I'm going to do 5.5% of my cost A, I would have to multiply A by 0.055. That is what gets added to the cost of the tickets. So I'm actually going to have my total cost is equal to 1.055A. That is the cost of my A plus 0.055 times A to get me my sales tax. So it's 105.5% of my A. Then I also have to add my flat fee of $8. So just in case, I'm going to put a little note here letting you know where this comes from. This is from my cost A plus my sales tax times A. It's just combined into one term, just in case you didn't see where that came from. Here is a function representing the total cost for buying $8 worth of tickets. So now part C is where we actually are going to get into the function composition. Part C says find T of C of X. So the first thing I would do is rewrite it as T with C of X plugged into it like that. So our C of X was what we did in part A. That was just 60 times X. So I get to plug 60 times X into my function T. And so I'm going to get 1.055 times 60x plus 8. And then if I simplify that, I get 63.3x plus 8. So this is my function T of C of X. And now for part D, we're going to evaluate this for a particular value of x and then interpret what that means. I guess I'll write it down here. We'll have part D. Let's find T of C of 6 and interpret the meaning. So to find T of C of 6, I just have to plug 6 into the function I just found in part C. So we get T of C of 6 is equal to 63.3 times 6 plus 8, which when I multiply all of that out, you're going to get 387.8. And now we have to interpret what this means. What was this problem even talking about? It was the cost of tickets for a show. So we're buying 6 tickets. The total cost for 6 tickets would be $387.80. That includes the taxes and the fees. All right. I think we're starting to get the hang of this function composition. So let's just do one last example to wrap it all up. The last example. Given the function m of x, which is the cube root of 5x plus 1, find two functions, f and g, such that m is equal to f of g of x. Now, there's a lot of correct answers to this, but I'm going to show you the way that I think of this particular problem, and I think it's the easiest way to do this problem. When I look at this function m, I see that I have a cube root on the outside, and then there's a bunch of stuff on the inside. Remember, I've been talking composition this whole time, talking about an inside and an outside function. So f of g of x, g is the inside function, f is the outside function. So if I take g and set it as all of the stuff under the square root that's inside the square root, or cube root, I apologize, it's a cube root in this problem. And then I set f of x to be the cube root of something. Well, then if I do f of g, I would take my function g, 5x plus 1, and plug it into this cube root function, giving me exactly what I want. So this is the way I would do it, because then f of g is equal to f of 5x plus 1, which is the cube root of 5x plus 1, exactly like we wanted. So I like to do these problems by viewing it as an inside and an outside function. There are other ways to do this problem and still get a completely correct answer. I'm just showing you one way which I feel is the easiest way to do them. Thinking about it in this way as well can also come in handy in calculus when you learn about something called the chain rule, which also involves derivatives like I mentioned earlier. So there's a lot of skills in this particular video that you might need once you move on to calculus. So it's good to get your questions out now and get these skills down real well. If you have any questions for me, you can feel free to drop them below. If you are a current student, feel free to ask in office hours or through email as well, and I will get back to you as quickly as I can. and I will see you guys on the next video.